Hey everybody in Pre-Car World, Mr. Pike here. I'm going to help you out with the section 1.5 or 1.3 1.5. First thing we're going to talk about, I'm just going to get right into it, is the greatest integer function. This is brand new to you guys. It's pretty cool. I like it. I like it a lot. Anyway, greatest integer function. All we do for this is essentially we take any values and we round down to the nearest integer. No matter what, we're always going to round down. So say we had like the greatest integer less than or equal to 2.1. The greatest integer of 2.1 would just be 2. So 2.1 rounds down to 2. Even if we have 2.8, the greatest integer that it rounds down to is 2. No matter how close I get to a number, so say I'm at like 3.999, I am incredibly close to 4. However, that still is going to round down to 3. The only time you really got to be careful with this stuff is say if we have the greatest integer of negative 1.2. Common sense sometimes tells you we need to round down to negative 1, but if you think of it on a number line, we have 0, negative 1, negative 2. Negative 1.2 is right there. Well, the number that rounds down to is actually negative 2. All right, so now that we know that it rounds down, let's try to see what the graph is going to do. So at 0, let me zoom in just a little bit. Oh yeah, big graph. All right, so at 0, when x is 0, the greatest integer of 0 is just 0. So I will be at 0, 0 for my first point. Any time between 0 and 1, that value is 0. So that's going to stay right there. But as soon as I get to 1, the greatest integer of 1 is 1. Likewise, the greatest integer of 2, when x is 2, is 2. 3 is 3, 4 is 4, 5 is 5, so on and so forth. And those are going to be whole values. Getting to those values, though, right, I have everything between 0 and 1 that has a y value of 0, an output of 0. As soon as I get to 1, it jumps up. And in order to know that I'm representing that I am infinitely close to 1, but not right on it, I'm going to put an open circle there so that we know we're getting really close to 1. But as soon as we get to 1, it jumps up to the y value of 1. It does this to infinity. And beyond. Doo-ba-doo. All right, I'm going to finish the graph real quick. So it continues to infinity in both directions. It's doing the same thing forever and ever and ever. All right, let's talk about our characteristics. So the domain of this thing, remember the domain is just our x values that are included in our graph. Well, it goes left forever, so my least x value is negative infinity. Goes right forever, my most x value is infinity. So this is going from negative infinity to infinity. The range is a little bit weird, but it's not too bad. 0 is in my range, 1 is in my range, 2 is in my range, 3 is in my range, 4 is in my range, 5 is in my range. But I'm nowhere in between. So we did the greatest integer, it has to round down. So everything that's in my range is an integer. Greatest integer. Woo. So if I want to say that only integers are a part of my graph, what we can say is math notation like this, and I will explain this, I promise. This says y, this weird looking like E type thing, is an element of, this weird Z thing means the integers. So this reads, y is an element of the integers. This weird looking Z thing is mathematical notation. It's understood all over the world that this means the integers. All right, moving on. For our x-intercepts, we have a lot of them. We have everything between 0 and 1, but not inclusive of 1. So we can state this as an interval from 0 to 1 using interval notation. No, that's an interval because we have a bracket around that because 0 is included. So don't forget for me that this is interval notation. The y-intercept, it only crosses y at one point. Yeah, we have a point right there, but remember that's not included. So it only has one point at 0, 0. This is not even close to being continuous. So you can just say no, or no squiggle. I messed up. And then the end behavior for this thing is x is approaching infinity and then x is approaching negative infinity. So we have as x approaches negative infinity, what do the y values do? And as x approaches infinity, what do the y values do? Well, as x is going to the left forever, as it's approaching negative infinity, my graph is going down forever. So I'm going to negative infinity in that direction. As x approaches infinity, so it's going to the right forever, my y values are going to infinity in that direction. Cool. All right, we're going to look at the next concept. I'm going to walk you guys through one of these, and then you'll get to try some on your own as well. So with this, these are called piecewise functions. Essentially what this is taking two separate pieces of two different functions and putting them on one kind of function altogether. So these equations, they represent real life more than anything in the world. All right, if I shoot, well, how about man, weird leg, man, and he kicks a soccer ball, right? Soccer balls look like that and goes phew, 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 phew. Right, he hits a ceiling. So all the way up, this soccer ball has kind of a parabolic motion. As soon as it hits the ceiling, it bounces off, and it's not exactly a parabola, because if this were a true parabola, this would have completed its motion something like this. And if this side were a true parabola, it would have been coming from something like that. But we know the soccer ball has to go up at a parabolic motion because of gravity. It's pulling it back down. So it hits the ceiling, comes back down, and accelerates as it goes back towards the ground. So this is a piecewise function where we kind of have two separate parts of parabolas that represent this situation exactly. So kind of starting off easy with you guys, we have the line 2x plus 3 as long as our x values are less than or equal to 1. We also have the line negative x plus 4 as long as our x values are greater than 1. So say I just graph 2x plus 3. If I take that 2x plus 3 as a y-intercept of 3, so 1, 2, 3, the slope is up 2 over 1, so I will have a line something like that. Now this says only when x is less than 1. Well, x is 1 right here, so I do not want any of my x values, I do not want any part of that graph where they would have been greater than 1. So at 1, my y value for this function should be 2 times 1, which is 2, plus 3 is 5. So I have 1, 1, 2, 3, 4, 5. And it's the same thing, but I'm only taking part of that graph. Make sure you guys put some good points on there. Probably more than I did, so that you make sure you graph it right. So now, we did that part. Now we also have this negative x plus 4. Well, that would be the line where we have 1, 2, 3, 4, and it would go down 1 over 1. We'd have a line something like this. This one says, if x is greater than 1, well, at 1, that is right there for that line. I only want the values where it would be greater than 1 for the x, so I do not want any x values on my graph for that part of it where they would have been less than 1. So I only want to take from 1 over this point right here. If I plug in 1, that's negative 1 plus 4 is 3. So I'm going to start at 1, 1, 2, 3. It is open because I am just greater than. And then I will continue to do my slope for my line, graph the line. And again, put some more points on there so you make sure you're really accurate. But that is what the piecewise function is here. You could state domain, range, any of those characteristics for this thing. They may have more pieces to them. That's no big deal. You just have more parts to take. But you're just taking two parts of the graph, or sorry, this graph and this graph, only when these x values are true for each of them, and putting them on the same plot. It's really all a piecewise function is. All right, we have one more concept we're going to cover in this video. All right, the last concept we are talking about is discontinuity. Functions are not continuous. Remember, that just means that they have a break in the graph somewhere. And that just means they're discontinuous. I don't know what else to say. But there are three types of discontinuity that we are going to talk about. One of them is an infinite discontinuity. Essentially, at a given x value, so in this case it's x equals 2, and for this graph it's also 2, it is going to infinity on either side of that x value. Shortcut way to check for infinite discontinuity is if we take this x value and substitute it into our function, f of 2 equals 1 over 2 minus 2. Well, 2 minus 2 is 0. We have 1 over 0. If you get some number divided by 0, we cannot divide by 0. But some number would tell us it's an infinite discontinuity. So you would say this is infinite discontinuity at x equals 2. Right, so that'd be your solution. If it's asking what type of discontinuity is it. Another type of discontinuity is removable. You will learn more about this when you learn about 2.5, and this is actually called a hole as well. That's just, it's like, it looks like it goes through that point right there. I'm talking about at 3 here, but this point has actually been like removed from our graph, so it just doesn't exist there anymore. And we can tell this, again, if we take the x value and substitute it into our function. I know this one doesn't match the graph, I'm sorry, but the same idea. This will also be a hole at -3, and you will see the shortcut for telling when you will get that. So we will have 0 over 3 squared is 9, plus 3 times -3, so 9 minus 9 is 0. Anytime you get 0 over 0, that will tell us that it is removable. So you can say removable at x equals -3. It's at a given specific spot. Because if this one, if it asked us about, like, say, -6, we could find a value for -6, and it looks like it goes through -6. So -6, it would actually be continuous through that value. We're only talking about specific values. Jump discontinuity will only exist really, well, never mind. One of the times it will exist. We also saw a jump with our piecewise function, or not piecewise, no. Our greatest integer. These are a ton of jump discontinuities. So that's one function. Essentially, it's just jumping from one value to another. Can also jump with piecewise functions from one value to another. The way that we check that, notice this one, it says when x equals 0. Let me zoom in for you guys. Zoom in. Yes, we can see it better. Thank you. All right, so at x equals 0. If these are going to the same y value, so if they would be going to the same y value at that specific spot, then this would actually be continuous. And I'll show you an example in just a second. But we can check and see if f of 0 is the same for both of them. So we'd have 0 plus 1 would be 1, and 0 plus 4 would be 4. These values are not the same, therefore we would have a jump at x equals 0. That would be a discontinuous jump at x equals 0. And we can see by the graph that this is a jump. The type of graph I'm talking about where it'll be continuous is, say we saw something where we had a function there, it's going let me graph it, beautiful, and say it does, I don't know, something weird there. All right, so if we had a function, I'm just going to take a stab in the dark here, I'll make this, oh poo, it meant to be that, fancy curl, I'm sorry, x squared plus 1 and x plus 1. If x less than 0, x greater than or equal to 0, if, and we're going to check it when x is 0. So if I plug in 0 to both of those, so f of 0 equals 0 squared plus 1, which is 1, and 0 plus 1, which is 1. See how they have the same y value? If they have the same y value, and you can actually tell by the graph, I could have drawn this all without picking up my pen. Therefore, that is a continuous function. There's no break in that graph. All right, hopefully this video has been helpful for you guys. As always, we are here for you, all of us pre-cal teachers, me, and whoever else is teaching pre-cal right now. We all love you, and we will see you in class for your questions. Bye-bye.